Hello, I am Sridhar Chitta. In a set of two videos, I shall discuss the basic action of a differential amplifier, which is the heart of the operational amplifier, using a unified approach to electrostatics and circuits. I express my sincere thanks to Professor V. Kamaraju, retired Principal and Professor, JNTU College of Engineering, Kakinada, Andhra Pradesh. His experience in using differential amplifiers for research helped me enrich the presentation of enhancements to the basic differential amplifier scheme to reject common mode signals and noise. I begin part 2 with a continuation to the description of a basic scheme of a differential amplifier of part 1. Then I shall discuss the physical aspects of the differential mode and common mode action of the amplifier and demonstrate its rejection of common mode signals. Then a discussion of the electric field components in the amplifier is followed with enhancements to the amplifier to enable it suppress common mode output voltages efficiently. In the previous video part 1, we learned the nature of differential mode and common mode currents and their origins. We then studied the principle of a U-tube manometer whose action is analogous to that of a differential amplifier. We concluded with the design principle of the operational amplifier and introduced the differential amplifier, which is the first stage of an integrated operational amplifier. The animations in the video are useful as an aid to visualize the circuit processes in the operation of the differential amplifier. We have not shown the surface charges that are present, which enable the conduction processes in the components for the sake of clarity. It is recommended that the viewer refer to the two videos 1 and 2 listed in the references at the end of this video, which provide a comprehensive description of the role of surface charges in enabling conduction in electrical and electronic circuits. We discussed the scheme 1, which uses bipolar transistors to make a differential amplifier at the end of the video part 1 of 2, and noted there will be no current if the signal voltages are 0 and the output voltage at the collectors of the two transistors will remain at plus VCC. There cannot be a collector current. We may consider replacing one of the transistors in scheme 1 with a PNP transistor, in which case a conducting path through the base emitter of the NPN transistor will be established. However, in the absence of a quiescent current to establish an operating point in the active region of the transistors, no useful linear amplification will be produced. If we connect the two emitters to the negative terminal minus VEE of the power supply, we can establish a conducting path for a quiescent current for the two transistors. We modify scheme 1 by including a conducting path to minus VEE for the two emitters and call the arrangement scheme 2. The animation in the following frames shows the current of mobile electrons injected by the emitter and appear to move with a constant drift speed, which is not so in reality, especially in the bulk neutral regions where it is the drift speed which increases and decreases. The current of the constant density electrons in the bulk neutral regions of the collector and emitter and in the resistor are not shown. The following animations show the currents in the amplifier to a differential signal, a common mode signal, and a differential signal in reverse. First, we add a conducting path to the emitters of the differential amplifier scheme 1. A differential mode signal voltage is now applied. The current is greater in transistor T1 than in T2. The sum of currents in T1 and T2 flows in the link to minus VEE. The differential signal is made stronger. The current in T1 increases and that in transistor T2 decreases. The sum of currents in T1 and T2 remains the same. We will observe the response of the amplifier scheme 2 to a common mode signal. A common mode signal voltage is applied and increased in strength. Note the increase in current. A differential mode signal voltage is applied with reverse phase. The current is greater in T2 than in T1. The sum of currents in transistor T1 and T2 flows in the link to minus VEE. The differential signal is made stronger. Current in T2 increases and that in T1 decreases. The sum of currents in both the transistors remains the same. It is the action of equal and opposite current changes in the collectors which makes this a differential amplifier. The conducting path to minus VE gave life to the amplifier of scheme 1. Now, there are several ways to bias common emitter amplifiers and establish the quiescent collector current. We examine self-bias or emitter bias and check its suitability for the differential amplifier. This method is suitable for most audio and other not so high frequency applications. However, if the amplifier is required to amplify signals from DC to several megahertz, then this biasing scheme cannot be used because of the bandwidth limitations introduced by the coupling capacitor CC and the bypass capacitor CB. The coupling capacitor CC is used to block signal DC voltages from affecting the quiescent conditions of the transistor. The bypass capacitor CB is introduced to allow a free path for signal currents to circuit 0 or ground and prevent reduction in amplification in its absence due to negative feedback by the emitter resistor. To increase bandwidth, especially in the low frequency range, the gain at these frequencies may be increased by increasing the size of the capacitors CC and CB. However, increasing the size of the capacitors amplifies the unwanted drift signals too. Drift occurs in transistors due to variations of HFE, VBE, and ICB0 with temperature. A shift in any of these quantities changes the output voltage and cannot be distinguished from a change in input signal voltage. To learn how this happens, see the NPTEL video lecture Cascading Direct Coupling by Professor K. Radhakrishna Rao. Dual polarity power supplies offer several advantages in realizing novel biasing methods over self-bias and are easy to implement in integrated circuits or ICs. In ICs in which it is not possible to integrate capacitors, the use of a single emitter resistor with a dual polarity supply to fix the quiescent emitter current permits the signal source to be grounded and also directly coupled to the amplifier, eliminating the need for a coupling capacitor CC. To learn how this is possible, see the NPTEL video lecture Cascading Direct Coupling by Professor K. Radhakrishna Rao, Lecture 22, Transistor Biasing. Even so, the problem of drift remains. The small base current through the signal source ground adjusts itself with a VBE of 0.63 volts to set the required quiescent emitter current. See the above video lecture 22, Transistor Biasing. However, the nuisance of the drift voltage amplification still remains, and we will now examine methods which integrated chips afford to eliminate this. In integrated circuits, we can make a differential amplifier using a pair of transistors with identical characteristics. If the HFE, VBE, and ICBO changes due to temperature of one transistor, so does an identical change occur in the other transistor because they are constructed on the same wafer. Therefore, the changes will cancel and the output will not vary. Parameter changes produce a common mode voltage which is rejected by differential amplifiers, as we shall soon see. See the NPTEL video lecture Cascading Direct Coupling by Professor K. Radhakrishna Rao, Cascading Direct Coupling, from the 39-minute. Having developed Scheme 2, borrowing the principle of operation of the YouTube manometer, it may seem we are lost in a labyrinth of transistor junctions, resistors, and closed current paths. The true elegance of the scheme will become apparent when we put in some numbers into our circuit. A simulation in TINA was made and the results are shown next. The Scheme 2 was simulated in TINA software. Two NPN transistors, T1 and T2, were connected in the differential arrangement. The collector resistors were chosen as 1 kilo ohm. The emitter resistor used is 1 kilo ohm. Two power supplies of 10 volt each with plus and minus polarity were used as plus VCC and minus VEE. The table depicts the currents in the two transistors for differential signal voltages which were varied. All voltages and currents shown in the table are instantaneous values. The quiescent current in the transistors is 4.6 milliamperes each when the voltages Vs1 and Vs2 are equal to 0. We assume that the emitter currents are approximately equal to the collector currents. Note that the current in the emitter linked to minus VE shown in the last column of table 1 has not changed when the differential input is changed. Also, the change in emitter current, see row 2 or 3, is the same in both transistors. It is this action of transistor current that resembles the YouTube manometer operation, in which the amount of liquid in one limb is equal to the fall in the other limb. From the values in table 1, note that when Vs1 is equal to minus Vs2 and equals 5 millivolts effective, the change in effective value of differential mode current in comparison to the current when no signal is applied is IE1 equals minus IE2 equal to 0.8 milliamps, assuming the transistor characteristics are identical. The reference directions of IE1 and IE2 are given by the circuit analyst. How can we interpret this action? We slightly rearrange the current arrows and note that the current change in emitter 1 continues through to emitter 2. The subtle point is that there is no differential mode current in the emitter link to minus VEE. In case you missed the differential action of the current, Review the previous frame and note how the curved arrows of emitter current seem to indicate the flow of the liquid in the U-tube manometer when subject to a differential pressure. Also, if the pressure above the liquid in both the limbs is the same, there is no difference in levels of liquids in the two limbs of the manometer. And analogously, if the differential signal voltage is 0 in the differential amplifier, the differential mode current components are 0. The fact that there is no differential component of current in the emitter link to minus VEE has another interpretation. We will learn about that important aspect a little later. We have developed, it seems, a reasonably good differential amplifier. The currents in the resistors RC vary proportional to the difference between Vs1 and Vs2. The voltage drops across the resistors RC will vary following these current variations to produce a faithful amplified version of the input signal. We will now check whether the differential amplifier scheme 2 will suppress common mode output voltages. We must remember that the primary objective the operational amplifier must fulfill is to amplify the differential input signal DC to whatever the transistor bandwidth permits and should suppress or at least minimize unwanted common mode output voltages due to common mode input voltages which may ride on the differential signal and produce output distortion. We will now observe the effect a common mode signal has on the differential mode signal. A differential mode signal voltage is applied. The current in transistor T1 is greater than in transistor T2. The sum of currents in T1 and T2 flows in the link to minus VEE. A common mode signal now superimposes on the differential signal. Current in both T1 and T2 increases. Note that the sum of currents in T1 and T2 has increased. With a common mode signal superimposed on the differential mode signal, we note an increase in current in both the transistors. We assume that the emitter currents are approximately equal to the collector currents. There is a subtle point to be recognized regarding the common mode current. Note that the charges of a common mode current are charges of the same polarity propelled towards each other to be repelled by one another, different from the situation of charges moving around in a circuit from a plus terminal towards the minus terminal where they can reunite. Because the common mode current is zero in the source and the load, the energy is dissipated in the resistances as infrared radiation or radiated away in other frequencies, say radio frequency in the connecting circuitry. For more details, refer to the articles at the bottom of this frame. Table 2 shows emitter currents of a simulation in TINA with a fixed differential mode input signal and varying common mode input signals. When different common mode input signal voltages are applied, the current in the emitter linked to minus VEE, shown in the last column of table 2, changes. Consider the superimposition of a steady or slowly varying common mode signal on the differential mode signal. The quiescent current is affected. This is evident in the changes observed in emitter current. See columns 7 and 8 in the third and fourth rows of table 2. The change in emitter current is indicative of a shift in the reference for the differential mode signal. We will soon learn that even though the quiescent current is affected, the differential current component is not affected. In the analogous U-tube manometer, it is as if the quantity or density of liquid in the limbs was changed due to maybe a change in density or expansion caused by variation in ambient temperature, and may go unnoticed if the U-tube inputs are always subject to a differential pressure. The manometer readings will then record a larger or smaller differential pressure than the true differential pressure and will be erroneous. In the web pages calrite.com or merian.com, U-tube manometers and how erroneous readings are caused in them are discussed. A steady application of a common mode signal on the desired differential mode signal resulted in a change in current in the resistors RC. It is this common mode component which will produce an error in the measurement of differential mode signals. Is there a change in the differential component of the current? Subtracting the sum of the common mode components in columns 7 and 8 from the sum of the differential mode components in columns 5 and 6 of the two collectors in table 2, we note the result is 9.2 milliamps in each case as shown in the table. Therefore, the differential mode component of current is intact. But the differential output voltage VO1 minus VO2 is affected. In a simulation run in TINA, the following values of differential output voltages were observed with a differential input voltage of 5 millivolts and common mode voltages as shown. Externally induced common mode voltages produced by differential to common mode conversion on the conductors of a twin lead cable are amplified by the differential amplifier as a voltage rise or dip across RC. See the discussion in Origin of Common Mode Currents, a Theoretical Perspective in part 1 of 2 of this video set. Such signals will cause differential mode signal distortion and maybe even clipped output voltages, since these signals can drive amplifiers into nonlinear regions of operation. If we can minimize the common mode currents by some means, it could serve to improve the fidelity of the differential amplifier response and also permit DC input signal coupling with cancellation of interfering common mode voltages due to VBE drift variation. We can use a resistor in place of the direct connection to the minus VE terminal of the power supply as one possible means to limit the magnitude of common mode current. This is shown in scheme 3 next. A common mode signal is superimposed on the differential signal. The common mode current in both T1 and T2 increases. A resistor is used in place of the link to minus VEE. The common mode current decreases. The sum of currents in T1 and T2 is decreased. Whether a shorting link or a resistor RE connects the emitters to the minus VE terminal of the power supply, the return path for the common mode current is to the point of lowest potential, namely minus VEE. we depict the electric field components driving the quiescent, differential mode and common mode currents in the figure. The directions of the differential mode field components are shown using brown arrows, and the common mode field components using red arrows. Note the absence of the differential mode field component in RE. We have verified that the differential mode current changes are the same in the two emitters, ensuring constant current in RE. In Table 1, this is verified directly, and in Table 2, we subtracted the change in emitter current from the total emitter current. Therefore, the voltage drop change across RE is 0 for the differential mode signal, and it is the common mode current which the circuit had increased in RE. In the small signal analysis of the amplifier, refer Chapter 3, Textbook 4 listed in references at the end of this video. In the differential mode, RE can be replaced with a short circuit to ground. For more details, refer Textbook 6 listed in the references at the end of this video. Noting that there is no voltage drop change across RE for the differential mode current component, we can increase the value of RE to reduce the common mode current, which is driven by the common mode component of the electric field. This can be justified using the equations 2 and 5 from the video part 1 of 2. If Vs1 is equal to Vs2 equals Vs, which are effective values, then using the equations 2 and 5, we obtain Vd is equal to Vs1 minus Vs2, which equals 0, and V output is equal to Vo1 minus Vo2 equals AC multiplied by Vs. However, if Re is equal to infinity, then because of the symmetry of the circuit, we obtain IE1 is equal to IE2, which equals 0, where IE1 equal to IE2 are effective values. If IB2 is much smaller than IC2, then IC2 is approximately equal to IE2, and it follows that V output equals 0. Hence, the common mode gain AC becomes very small, and the common mode rejection ratio is very large for a very large value of Re and a symmetrical circuit. Note that Re equal to infinity should be interpreted Re equals a large resistance and not as an open circuit, so that a path for the quiescent current exists. If the operating currents of the transistors are allowed to decrease, this will lead to higher HIE values and lower values of HFE. Both of these effects will tend to decrease the common mode rejection ratio CMRR, which we desire large. Sensing serious problems in increasing Re, engineers, by a stroke of genius, replaced the emitter resistor Re with a constant current source, as we shall see in Scheme 4 next. With its large output impedance and maintenance of a constant current, the common mode current could be brought down to a minimum, while the common mode voltage was absorbed by the reverse bias of the constant current source's collector junction. We once again note how the differential amplifier action for current replicates the analogous U-tube manometer differential action for pressure. A common mode signal is superimposed on the differential signal. the large resistor Re reduce the sum of currents in T1 and T2 flowing to minus VEE. We can use a constant current source and almost eliminate the common mode current. Using a constant current source, almost no common mode current is seen. We will now discuss a few frequently asked questions on the implementation of differential amplifier circuit designs. How are input base currents and the cut-in voltages of the transistors established to enable their operation in linear active regions? When the sensor inputs are physically connected to the differential amplifier inputs, base current paths via signal ground are established. The emitter terminals will be minus 0.63 volts to the base terminal due to minus VEE, and quiescent currents flow in the transistors. The schemes 3 and 4 are called emitter coupled or long-tailed pair, which use the constant current method of biasing. The viewer may refer to the articles listed below for descriptions of biasing techniques of differential amplifiers and signal processing. Does the differential amplifier necessarily need a dual polarity supply? The fundamental issue is if the signal is to swing both positive and negative with respect to common, this zero signal reference voltage must be at a fixed level between the supply rails. For more details, refer to the article at the bottom of this frame. The principal advantage of dual supplies is that their common connection provides a stable, low impedance, zero reference. The two supply voltages are usually equal and opposite and often tracking, but that is not an absolute necessity. With a single supply, such a node must be created artificially by introducing additional circuitry to provide some form of biasing to maintain signal common at an appropriate mid-supply voltage.